Linear regression is a way of modeling relationships between quantitative variables. For example, here is data consisting of pairs of values in a scatter plot of the data. Modeling this data means coming up with a formula for estimating one variable as a function of the other. This input uses the linear model fit function to model the data using a straight line, and here is a plot of the data and the line. The first argument in linear model fit is the data, the second argument is a list of functions, and the third argument is the variable of those functions. The model is called a linear model because the model that is fit to the data is a linear combination of the functions listed in the second argument. In this example, those functions are 1 and x, so the model is the sum of a constant and a multiple of x, which is a formula for a straight line. In the plot, the value of the constant is the point called the intercept where the line crosses the vertical axis, and the coefficient of x is the slope of the line. The linear model fit function by itself returns a fitted model expression, which is a data structure that contains the output of the linear regression calculation and provides for efficient calculation of other results. One of those results is the formula for the best fit, which is obtained by following the linear model fit expression with best fit enclosed in square brackets. The string best fit is referred to as a property of the fitted model expression. This uses the best fit parameters property to get the intercept and the slope coefficients from the formula for the best fit. The best fit line is computed using least squares regression, which means that the line is chosen to minimize the sum of the squared differences between the line and the data. Those differences are called residuals. This input uses the fit residuals property to get the list of residuals. The residuals are a measure of how close the line is to the data and can be used to compute various measures of the quality of the fit. One of those measures is the coefficient of determination r squared, which came up in an earlier section. This input gives r squared for the model in this example. R squared can be computed using the formula for r from the earlier section, or that formula can be rearranged with a bit of algebra to get a formula for r squared in terms of the variance of the response y and the variance of the residuals. This way of writing the formula for r squared leads to interpreting r squared as a measure of the proportion of the variation in the data that follows a straight line, or that is explained by the line. The variance of the independent variable y is a measure of the total variation in the data. The variance of the residuals is a measure of how much of that variation does not follow a straight line, and the difference between the total variation and the variation in the residuals is a measure of how much of the total variation does follow a straight line. Dividing that difference by the total variation gives the proportion of the total variation that is explained by the line. If all of the data points fall exactly on a straight line, then the coefficient of variation is 1, indicating that all of the variation in the data is explained by the line, and any difference between the data and the line results in a smaller value of that proportion. Here is that calculation of r squared for the data in this example. This picks out the values of the independent variable y, and this does the calculation of the coefficient of variation r squared. The result is the same as the value computed earlier.